Bismillahirrahmanirrahim. Good morning. Today, I will try to do appropriate summary, simple summary to this article. Our article's name today is Adiabatic to non-adiabatic change in the conduction mechanism of zinc doped. That means we will use zinc like a doped symbol by use two different concentration, and after that we will start to calculate, and actually not calculate, but we will start to note the difference between these few plots. Okay, zinc doped with this structure to perovskite. Let me go to the first one and start to do our summary. They reported what? They reported the results of electrical transport properties of this structure with two different amounts of zinc doped, 100%, 200% bulk. Our sample here in this article is bulk sample. And after that, there will be some change to it. I will explain that in the next slide. Bulk samples prepared by what? Solid state reaction. Brought over a wide period of temperature from 5 to 300 Kelvin, but with presence of a magnetic field. We will know that in the next plot, we will dealing with three different amounts of magnetic field, 1, 2, 5 Tesla. After that, the temperature dependent on the resistivity data were fitted using Morse and variable range hopping at 100% of zinc, the doped sample, from a period amount start from 235.5 to 300 Kelvin, and with 200% of zinc doped samples start from 133 to 300 Kelvin. Here we noted that I know that's early, but let me say that here the period of temperature is bigger than the previous one when the zinc was 100%. Okay, from 235.5, but started. But here with zinc 200%, 200% started from 133. To calculate what? By using the variable range hopping with these different concentration of zinc doped to calculate the hopping distance and density state near from Fermi level. Here, let's take a look what that's VRH, like I said before, variable range hopping. What that means? Let's give appropriate definition to it. I take this definition from Google and I put it all the links in the last slide of this article. You can take a look. Is a model used to describe the carrier transport in a disordered semiconductors and or in amorphous solid state. And we can use this model to describe the carrier transport in two different situations, disordered semiconductor or in amorphous solid state, by hopping. Hopping, that means something like jump in an extended temperature range. The temperature dependent on the resistivity data were also fitted using SPH, the small polaron hopping model. Let's take a look what that means. Small polaron hopping is a type of conduction mechanism which single valid activation energy is valid. That's mean it's a simple. It's a type of conduction mechanism, or one of type to mechanism, conduction mechanism, but when the single valid activation energy is valid. That's mean the valid activation energy is something like condition. We must have valid activation energy by using the small polaron hopping, which contribute the carriers to hop, to jump at the neighbor site. What is the polaron? It's a conducting electron in an ionic crystal together with the induced polarization of surrounding wire and surrounding lattice. That's mean it's an electron, conducting electron in ionic crystal together with what? Together with the induced polarization of surrounding lattice. Now, I said at the first slide in this lecture, adiabatic and non-adiabatic. What does mean adiabatic? That mean the simples will act with constant temperature without, we will not note any change, or not change more change, will not note more change in the temperature. But the reverse situation with the non-adiabatic, because the simple will act change in the temperature curve. Now the adiabatic with simple polaron hopping conducting is followed for 900% doped, while a non-adiabatic with or by using small polaron hopping conducting is active for 200% to all the fields. Here, the bonds shape will be like that. The oxygen will act the rule like a bridge between these two manganites and between the doped simple and the manganites. Here, the introduction. The closal magnetic resistance effect can be explained by the double exchange model. I explained that in the previous lectures. The presence of the manganite ion with different valence is essential, is important to double exchange. At this structure, like we know, we have two bond, two level, the low level and the top level, T1, T2. And we will talk about by using these two levels and which one will be full, which one will be empty. To count this process to jump, hopping, that means the electron will jump from level to level, from side to side, but need energy or heating, that's mean increase the temperature, or make the distance between them be shorter. All of these is parameters, important parameters. When we say we'll study hopping electron, that means we will focus on all of these three. And sure, we will note one of them is happen. Now, let me keep going. Yes, because of the absence of the manganites, 4+ ions. Here is important note: without double exchange and this parent structure, the Se between the manganites 3 plus ions is dominant. What that's mean here, SE, super exchange, with absence of the double exchange. At the Mn manganese 3 plus, the super exchange will be dominant. And the activation type, conduction, prevails due to the here the T1 will be full electron, but the T2 will be empty. The substation of traveling that's mean with 3 containants. Lanthanum ion by a divalent alkaline air. Divalent that's mean has 2 contents. Cases the conversion of the jump of the manganese 3 plus to manganese 4 plus between this travalent lanthanum and divalent ion, which leads to what? Which leads to ferromagnetic metallic state. From paramagnetic, from non-ferromagnetic to a ferromagnetic metallic state after the substation or the relation, the action between the travalent lanthanum and divalent alkaline earth. We have ferromagnetic metallic now, having a closal magnetic resistance near from isolating metallic transition, having a closal magnetic resistance near from the isolating metallic transition, which has been mediated by double exchange mechanism. That's mean here in this article, in this processing, we have 2 mechanisms: super exchange between Mn and M3. Let me take a look, it's important. Super exchange with Mn3. And here between these 2 different charge, 3 plus to 4 plus, we have double exchange. There is a shift in the Q temperature from 368 to 361. That means some little decreasing from 368 to 361 Kelvin. Here, from bulk, here, I noted from this article, the simple shape is changed from bulk to nano size perovskite samples, as the grain size of bulk to nano perovskite samples change from 0.65 to 16 nanometer, respectively. This reduction in grain size corresponds to decrease in a transition form from ferromagnetic to paramagnetic. Suddenly, now we say the shape, the simple shape is changed from bulk to nano size perovskite. Why? Because here we have some reduction in grain size corresponds. Why? To a decrease in transition form from ferromagnetic to paramagnetic. Here, the characteristic is changed from ferromagnetic to non-ferromagnetic after the simple shape is changed from bulk to nanoside perovskite. Here, our topic started from here. These 2 important plots. This structure with 100% concentration of zinc, the doped sample. Here, with 200% zinc doped. Here, we have, like I said, at the first slide, this concentration, this process, this calculations will be with presence of magnetic field. We have three different amount of magnetic field to all of these two different amount of doped concentration, 1, 2, and the last one is 5 Tesla. Here, 1, 2, 3, 5, we noted at 1 Tesla, it's recorded the higher result of resistivity. And after that, when increase the magnetic field, the resistivity started to decreasing. Here, the major point at 300 Kelvin, all of these three different colors, curves, three different amount of magnetic field be together at 300 Kelvin. Here we have isolating temperature, isolating metallic transition temperature, approximately equal more than 175. The period between the starting point and last point to all of these three curves is a start from 0 to 300. After that, the major point started here at 300. That means the resistivity increasing in the top, and after that decreasing. And the same thing, if you cooling the sample or heating the sample, that's dependent on it. Here at 100% concentration, sure, we have isolating metallic transition, but it's approximately 75 Kelvin. It's less than the previous one. The period between the major points at here approximately less than 150. It's smaller than the previous one. The major points started at less than 150 Kelvin, and after that act like all of these lines, all of these different amount of magnetic field act like a line, like a constant temperature, constant with with increasing amount of the resistivity, sorry, acts constant with the temperature after the, let me say, 140 Kelvin. Here is some important table increased to us by calculating all the numbers or the important numbers from these previous plots. When increasing the magnetic field, resistivity will decrease, let me say will decrease, and both of the hopping distance and hopping energy will decrease too. All of these three elements will decrease the resistivity, hopping distance, hopping energy, except what? Except the density of state near from Fermi level just will increase. This adds the first three lines explain to us these results, but at the 100% of zinc. But here at the next part from this column explains to us the results at 200% of zinc doped, when increasing from 1 Tesla until 5 Tesla, what will happen? The same thing, the resistivity and hopping distance, and the last one, hopping energy, will decrease too, except the density of state near from Fermi level will increase. But that's mean the resistivity is decreased, that is decreasing, that's mean the conductivity increase. Because what? Because the density of states near from Fermi level is increasing. That's mean the relation between the conductivity and density of state near from Fermi level. Now, the electronic properties of a system are driven by what? Are driven by the induced distortion effects. Induced diffraction effects driven the electronic properties. Due to what? Due to the presence of two different valent transition metal elements, Mn and Zn. Due to what is important? Because here we dealing with two different transition metal elements, to manganite and to zinc. We have two different isolating metallic transition, two different amount, these parameters, these symbols are manganite and zinc. Here we have temperature, Lin resistivity to these two different concentrations at 1, 2, 3 Tesla. Here the curve acts like line, except this simple curve. This line, the researchers could to calculate this line by use some math equation to calculate the slope, and after that could to plot all of these three lines. The same situation here, but with some difference. For example, here the started point to the all of these three different amount of magnetic resistive of magnetic field started from here until approximately 1 here, approximately -1 or maybe more than. That's mean here it's some different amount about the resistivity at this concentration and the next one at 200%. Here started from 3 to 8. That's mean here it's a bigger amount from the previous one. At the temperature, here until 0.3, here until 0.26. Some simple difference between the temperature between these two plots. But here, we have major point at approximately less than 0.27, but here we don't have something like that. Here the resistivity, Lin resistivity is more than at 100%. Here started from 3, here started from approximately -2. The last plot in this lecture is that with Lin resistivity divided on temperature at y-axis and at x-axis temperature Kelvin to reverse to force -1. Here, the Lin resistivity started from -10. The starting points, I'm talking about the starting points, and here -8, and reached to approximately -6. Here, the results, it's more than the previous one, because here from -2 approximately reached 7. What about the temperature? The temperature here started from 0 until 14.10 to force -3. Here it's less than. They used the same amount of magnetic field, 1 to 5 Tesla. Here we have major point approximately at 6.10 to force -3. But here we have with just 1 and 2 Tesla. At 5 Tesla, the situation is different. They could plot these lines by using some equation math to calculate the slope. Here, actually, this column, it's not important to me because it's not related with my topic about the magnetic field and the closal magnetic field or closal electric resistance. Closal magnetic resistance, I'm sorry, and closal electric resistance. Here the conclusion, both samples show orthorhombic at these two different amount of doped concentration, orthorhombic crystal symmetry for the zinc doping at the 100%. The temperature started from 253.5 to 300, but less than with increasing the doping concentration, started from 133. The variable range hopping model is found to be valid. It's a condition, like I said in the previous lecture, and the previous slide. By increasing the zinc concentration, the hopping energy and hopping distance are increasing, whereas except the density of stays near from Fermi level is decreasing, but with the effect of enhancing the magnetic field. That means the magnetic field must be found, we must dealing with the magnetic field when we want to do simple thing, simple situation, simple plots, simple calculations. It's a condition, the magnetic field. Here, but the density of states near from Fermi level increasing, where the hopping distance, hopping energy goes on decreasing for each sample. When increasing the concentration of doped sample, NEF will decrease. At the same time, NEF will increase when all of these other parameters will decrease. The same thing. Here was a non-diabatic with simple polar hopping conduction previous for 200%, 200% in range from 5 to 3 Kelvin. The adiabatic simple polar hopping conduction is observed at 100% doped. That means at the first plot, it was adiabatic at 100% zinc doped, but non-diabatic with 100% of zinc doped. Where the non-adiabatic, like I said before, it was found that all the parameters are symmetrically with the increase in the zinc concentration. Here, the last slide, after that, the sources slide. 100% doped from 235 Kelvin, 0.5 to 3 Kelvin, 300 Kelvin, and some What that means? That means when some relation between the concentration number of zinc with the temperature. When I increase the temperature, when I increase the concentration of zinc, the temperature period will increase because at 100% started from 235 to 300. But when increase the research, increase the concentration of zinc, the situation about temperature here is different. The temperature period is increased, started from 133 to 300. Maybe if they increase the concentration of temperature, increasing the concentration, of zinc, maybe the temperature approximately started from 0 to 3 Kelvin. That means some relation between the concentration of the doped with the period temperature. The activation energies and the electron-phonon coupling constant enhances due to the enhancement in the bandwidth with the zinc ion doping for both simple at all fields. Thus, there is a strong correlation. The strong correlation between what? Between a structural and electrical transport properties. Strong correlation between structural and electron transport properties in the system. That's it. The last lecture about the article's name, the author name, the published year, and many important things like that. If you want, can take a look. This is a slide about the simple polar unhopping, and many definition. I put it in this article. These sources, you can take a look to these sources to be sure. Thank you about your watching or listening. Have a good day. See you on the next lecture.